So far, we've seen a bit about central angles and inscribed angles and their relationship to arcs, as well as some definitions around chords. But there are some relationships between chords and angles and arcs that are important too. In fact, when we have an arc and a chord that have the same endpoints, we call the arc AB the arc of chord AB, and vice versa. So we name the arc based on the chord, and we name the chord based on the arc. So go ahead, pause the video, copy this down, come back when you're ready to move on. So when it comes to chords and arcs, there are three important theorems that we're going to see, one of which we're going to prove as a part of the video, the other two we're going to prove later. The first is called the congruent arcs and chords theorem. That says that in the same circle, or in two congruent circles, congruent arcs have congruent chords and congruent chords have congruent arcs. Now remember, the congruent circles are ones that have the same radius, so circles that have different size radii, this is not necessarily going to be true. We have to have two congruent circles, or we have to have chords or arcs of the same size in the same circle. So go ahead, pause the video, copy this down, come back when you're ready to move on to the next one. So the proof for this idea is actually not terribly difficult. It involves some triangles and the fact that radii are congruent, but that's going to be left to you as a part of your proof practice. Moving on, we have something that we call the bisected chord theorem. It says that the diagonal that is perpendicular to a chord bisects both the chord and the arc. In this case, we have chord and arc AB, and we have diagonal YZ. Well, what this says is that if ODA is a right angle, that is, that ZY and AB are perpendicular to each other, then AD is congruent to DB, and AY is congruent to YB as arcs. So go ahead, copy this down, see if you can get an idea for how we might actually go about the proof. Again, it does involve some radii, so you can go ahead and draw some radii there and start to look for triangles, because triangles are the way that we show congruent things. Come back when you've copied it down, done a little bit of planning on your own, and you're ready to see the proof itself. So now getting to the actual proof of this theorem, the thing that we know is that the diagonal and the chord are perpendicular. So we know that ZY is perpendicular to AB, and therefore that we have two right angles, ODA and ODB, that are congruent because all right angles are congruent. That's where we're going to start with this theorem. Well, now that we have two right triangles, ODA and ODB, proving the two right triangles are congruent, remember, is easier than proving other two types of triangles are congruent, because we only need two sides, or an angle on another side. Well, this is a circle, and we know that OA and OB are both radii of the circle, and because they're radii, that means that they are congruent. So OA is going to be congruent to OB, because all radii in the same circle are the same length. So radii are congruent. And we also know that we have this shared side, OD, between those two triangles, and OD is congruent to OD by the reflexive property. So now we have a right triangle in which we know the right angle, and we have two congruent sides. And importantly, because of the particular type of theorem that we're going to use here, it's the hypotenuse that is congruent to the hypotenuse of the other triangle, as well as one of the other sides. So the two triangles are congruent to each other by hypotenuse leg. And so therefore, triangle OAD is congruent to triangle OBD by the hypotenuse leg postulate. Well, now that we have that, we have basically everything we need to know about this circle in order to say that the chord and the arc are both bisected. So immediately from CPCTC, we can say that AD rather, and BD are congruent. That is because of CPCTC. That gives us that the chord is bisected. We can mark that off as something that we have shown. And now we want to say something about the arcs. Well, we can't say anything about the arcs directly because they're not a part of our congruent triangles. But we can remember that arcs and central angles are congruent. Congruent central angles create congruent arcs, and congruent arcs create congruent central angles, and recognize that we have two central angles in our two congruent triangles. Therefore, what we can say, moving up above the circle here now, is that angle AOD is congruent to angle BOD, also by CPCTC, our favorite application of congruent triangles. And because those two angles are congruent and they are both central angles, we know that the arcs that come from those central angles are congruent, so therefore AY as an arc is congruent to YB. And that's the congruent arcs theorem. Not to be confused with the corresponding angles theorem, but they have the same initials there, and therefore we have what we want. The diagonal that is perpendicular bisects the chord and the arc. One more theorem or idea to see, so if you haven't copied down this particular version of the proof, or if you didn't come up with this proof on your own, go ahead, pause the video and copy this down. Come back when you are ready to see the last idea, as well as do one quick practice problem. So the last thing we have to see related to chords is what happens when two chords are congruent. In this case, it says that in the same circle or congruent circles, congruent chords are equidistant from the center. Therefore, if two chords are equidistant from the center, they are congruent, and if the chords are congruent, they're equidistant from the center. In this particular case, it says that OD and OG, which must be perpendicular to the chord in order to be distance, OD being congruent to OG, means that AB is congruent to YZ, and vice versa. It works in both directions. So go ahead, copy this down, come back when you're ready to see a quick application of it, and end the video. So by using this, we can actually calculate the size of a chord, or the length of the radius, or the distance from the center of the circle. For example, we could know that we have a circle with center O and has a radius of 13 centimeters. We also could have a chord that is 24 centimeters long and want to find out how far from the center of the circle the chord is. You are welcome to pause the video and do this on your own if you can immediately see what we're going to do here. Otherwise, you're welcome to keep watching and just copy it down into your notebook as we go. Well, here we're told that the radius is 13 centimeters, so AO is 13 and OB is 13. We also know that the chord AB is 24. So the entire length of that is 24. That gives us an isosceles triangle, but it actually gives us something even better than that, because OD, being a part of a radius or a part of a diameter, is perpendicular to AB, which means, by the bisected chord theorem, because it's perpendicular and it goes through the center, that AB and BD are congruent, which means each of these is 12. And now we have these small right triangles, AOD and BOD, that we know the hypotenuse and one of the legs for, and now we can find the distance x. Well, the Pythagorean theorem says that x squared plus 12 squared is equal to 13 squared. And so we could go through with this calculation, get that x squared plus 144 is 169, x squared is 25, and x is equal to 5. You can verify those calculations on your own. Or we could remember that 12 and 13 form two parts of a Pythagorean triple of 5, 12, 13. And so whether we calculate it that way or we remember the Pythagorean triple, that chord is 5 centimeters away from the center of the circle, because a perpendicular segment through the center of the circle bisects the chords that it intersects with, and therefore we can use Pythag and these right triangles. So again, one more time, congruent chords make congruent arcs, and congruent arcs make congruent chords. That's the congruent arc and chord theorem. The bisected chord theorem tells us that the diagonal that is perpendicular to a chord bisects both the chord and the arc. That is true of radii as well as segments coming from the center of the circle, and that the congruent chords theorem says that congruent chords are equidistant from the center of the circle, and chords that are equidistant must be congruent.